Welcome back. Now, we've completed our round of experiments for Food Vision Mini deployment. We've trained two models, EffNetB2 and ViT, and we've found that they're both fulfilling our performance goal of 95+% accuracy. Now we're going to evaluate whether they're fast enough to be deployed. So let's jump in here. We want a goal of 30 FPS. That's the most ideal use case. Of course, faster is better. Comparing model results, prediction times, and size. So we've got two statistic dictionaries that's comparing a bunch of characteristics about each of our models. So one of the ways that we can turn these into a way to compare them is, of course, we could just look at them, or we could put them into a structured fashion. And you might have already done this by turning them into a data frame. So turn stat dictionaries into data frame. So df equals pd.dataframe, and I'm going to pass in here a list of our two stat dictionaries, EffNetB2 stats and ViT stats. And then we can add a column here for their names, for model names. So we'll just do it in the order that they appear. df model column equals EffNetB2 followed by ViT, just for short. And then while we're here, let's see what this looks like. Wonderful. Now I'm going to convert the accuracy to a whole number, just so it's a little bit more readable. So convert accuracy to percentages. We'll go df test ac equals round. So we'll round the test ac times 100 to 2 decimal places, and we'll see what that looks like. Beautiful. So we've got a little bit of a comparison going on here. So which model performs best on the test loss? Remember, test loss, lower is better. So it looks like our ViT model outperforms EffNetB2 on the test loss. It's got a lower loss value. Loss value measures how wrong your model's predictions are. And then test accuracy, higher is better. So it looks like the ViT model again outperforms our EffNetB2 model because it's got 98.5 or thereabouts versus 97%. So about a 1.5% difference on the accuracy. Higher is better there. Number of parameters. Now this is an interesting one. We've discussed, maybe we write these down. So which model is better for each parameter? We'll go test loss, lower is better, ViT, and then we want test ac, higher is better, ViT. And then we want to compare on number of parameters. Now this is a tough one because it's quite situational. So we've generally lower is better. Now, again, take that with a grain of salt because I'm going to put here, there we go there, and then go, sometimes models with higher parameters can still perform fast. So generally lower is better. If a model has more parameters, it generally takes longer to compute. So take that with a grain of salt. It's not always the case. So in this case, the best one would be EffNetB2 because it's got a lower number of parameters. And we see that this correlates to model size, because our model EffNetB2 with a lower number of parameters has also a lower model size. And if we had infinite compute power, we wouldn't really care about the model size because we could put it anywhere. But if we're trying to deploy to a mobile device, that's our task as the company of Food Vision, is to get our model onto a mobile device or a small device. We may have limited resources. So in the case of model size, we'd probably prefer a smaller model. Of course, this could change once we actually deploy it and we do some experiments. We might go, oh, we could try the bigger model. So for number of parameters, we're going to say that EffNetB2 model is better. So EffNetB2, and then we'll put here, and then we go here. What else do we want? Model size. So again, EffNetB2. So for our use case of deploying to a mobile device, generally lower is better, but if you had infinite resources, you could go the biggest, best model you could find. And think about back to a Tesla car. So Tesla car. Now, what sort of computer could you fit in this car? Well, you could fit quite a large one, but of course, you're still at some point going to be limited. The bigger you build it, the more weight that's going to be in the car. The bigger you build it, the more power it's going to draw, so it's going to drain the battery. So again, you're kind of thinking, how big is a machine learning model that I can run on this? You kind of want a trade-off. You want the biggest possible model that you can fit on there without it being too performance degrading, as in draining too much power and taking too long to perform. So we'll come back, we'll finish it off. Time per pred on CPU. So let's go time per pred CPU. Now these values might be different if you go to the GPU. Again, don't worry if your values here aren't exactly the same as mine. They should be in the same realm, so not too far gone. So if you have a value that's 10 times bigger or 10 times lower, 10 times bigger is probably a bad thing. 10 times lower is, hey, maybe you're running them on quite a fast CPU. They will differ whatever hardware you're running on. So we want lower is better, will be highly dependent on the hardware you're running on. So in this case, EffNetB2 wins out. Now, both of them, let's write this, both models fail to achieve our goal of 30 plus FPS, using Google Colab hardware, that is. However, we could always just try and use EffNetB2 and see how it goes. So let's do another little bit of a comparison here as well. So across the board, well, on the performance metrics, ViT is better, but on the inference metrics, EffNetB2 is better. So what would we favor if we're going to deploy to a mobile device? Yes, we would like the best performance possible, but our EffNetB2 model isn't that much lower in terms of performance metrics. Whereas these other metrics here, ViT is kind of on a much higher scale in terms of number of parameters, model size, and time per CPU. Let's find out the ratios, hey? So maybe we do a comparison. Compare ViT to EffNetB2 across the different characteristics. We've already done this visually, but let's find some ratios, characteristics. So I'm going to make another data frame here, PD data frame. And because I've added the model column, we can now index on that model column. So df.setIndex on the model, and then we want to locate the ViT index. And then what I want to do is divide that by df.setIndex. So divide it by itself. I've set the index to the model column, but this time locating on the EffNetB2 index. And then I want to set the columns. I need to put data in here actually. Now I want to set the columns equal to ViT to EffNetB2 ratios, and then I'm going to transpose it. Let's see what this looks like. Uninspected indent. What's happened here? Oh, I need an opening bracket. Wonderful. There we go. So what we're doing is we're just flipping this data frame around so that we can compare the ratios of ViT versus EffNetB2. So we can see that our ViT model, of course, performs better on the test loss, so a lower ratio here is better. The test accuracy is almost the exact same, except the ViT is slightly better. So we get 0.01 better in terms of ratios. But now here's where the comparison gets, the scale increases quite a bit. In terms of number of parameters, our ViT model is 11 times higher than our EffNetB2 model. And in terms of model size, it's also about 11 times higher. And in terms of time per prediction on the CPU, it's about 5.5 times higher. So the question we're going to ask, I'm going to pose to you, is looking at these numbers here, is the trade-off worth it? So for our ViT model, is the trade-off of having an 11 times bigger model and an 11 times larger model size footprint and a 5.5 times longer time per prediction, are these numbers worth it to gain these metrics in the performance? So from my point of view, I would say not really, because we're going to prefer a faster model that performs almost as well as our best performing model and has a much lower number of parameters and a much lower model size. Now, of course, this is going to be different depending on what problem you're working on. But for Food Vision Mini, we're going to optimize for speed. Our EffNetB2 model still performs quite well on the performance metrics. If these were way lower, like 70%, well, then we would definitely consider using ViT. But because they're so close and because these are so different, I'm going to say EffNetB2 model is our model of choice. This model to me satisfies our goals better than the ViT model. So we're going to push forward later on and deploy that EffNetB2 model, but there's one more comparison I'd like to do, and that's by making these ratios visual. So let's do that in the next video.